Good morning, everybody. Today we're going to be graphing polar equations. Kind of a fun lesson, um, and a lot of calculator work for the most part, but we are going to do some by hand just because it's good practice. But the really cool ones we're not going to be doing by hand, um, at least not for the, yeah, we wouldn't be doing it by hand, but I will be showing you how to kind of go about doing it, but you wouldn't be expected to do that yet. But really we're just going to practice graphing these in and kind of identifying the type of graph that they are based off of what you're given, also just by its shape. But some cool graphs coming today, and I don't say that sarcastically, so that's so hopefully you enjoy it. But just starting off, let's graph these. So if you eventually you might be able to identify these without needing to have it in polar coordinates, but that's probably not today. The first two you might be able to get without converting into an x and y rectangular equation. If not, that's okay. But if you remember from yesterday, r cosine theta is x, r sine theta is y, and then we also know that r squared is x squared plus y squared. Basically, those are the things that you need to know to get here. I want you to, first of all, sorry, haven't talked about this. This is traditional graph paper for polar coordinates, polar graphs. This is also an x and y axis. So you can graph both on this paper, but if you are graphing with the idea of radius and angles, it's a lot easier to just go with this. But should just look like a unit circle, kind of. Each of these lines is a unit of the radius. So if we wanted to count out to a radius of 3, 1, 2, 3, it's this circle that's radius of 3, and then you just have to find the angle that you're graphing. But yeah, I don't think we've actually seen this in this class. So if you haven't seen this type of graph paper, don't worry. It's should be intuitive for the things that we've been doing. But r of 3, if you want to think about this, where the radius is 3, well, the radius is 3 at 1, 2 at here, but the radius is also 3 up here. It's also 3 over here. It's also 3 over here, and everywhere else between. So here is where the radius is 3. And it doesn't say anything about anything else, so it's just this. But that seems kind of weird to make that jump. So if you aren't comfortable with that, we can change this into rectangular coordinates and a rectangular equation. From here, it doesn't feel like you should be able to, but if I square both sides, it'll make more sense. So if we do this, we have r squared equals 9. Over here we have r squared as x squared plus y squared. And this is an equation of a circle with center at 0, 0 with a radius of 3. So then if I wanted to graph that, it'd be this. So there's two different ways. This looks a lot simpler than this. Just because it looks simpler, though, doesn't mean it makes sense. So careful. But yeah, if you wanted just to graph from here, you're good. Now, where is the angle pi over 4? Well, the angle is pi over 4. First of all, this is in degrees, so sorry about that continuity. This is a pi over 4 at 45. Ooh, good start. So this is pi over 4. It doesn't say anything about the radius, so this ray right now is pi over 4. But because it doesn't say anything about the radius could also be negative. So at negative pi over, the negative angles would be over here. So basically it's a diagonal line. Now if I wanted to change this, I still can. So maybe it doesn't quite make sense from here, but just if theta is equal to pi over 4 and we wanted to change that into x and y, we want to introduce another piece that we know. The fact that tan theta is y over x. So tan theta is y over x. I'm going to plug in theta. So tan of pi over 4 is equal to y over x. Now tan of pi over 4 is 1. If I multiply by x, I get that x equals y, or y equals x. And this is an equation of a line where the slope is 1 and it goes through 0, 0. Here we have a slope of 1. It's kind of hard to tell that, but basically it's going through pi over 4. So pi over 4 is where x and y are equal. If you wanted to check the slope, that should be a slope of 1. Lines go through both directions, so again, kind of makes sense when you have it written like this. But if you didn't want to have to go through those steps, you could still graph it from this position. Okay. So quick note, if you're just given the radius, if you're just given an angle, it's going to look like one of these things. It's going to be a circle that's centered at 0, 0, or it's going to be a line that goes through 0, 0. Now that line could be different depending on the angle, but at that point you should be able to figure it out, but just by connecting 0, 0 to that angle and then extending it into a line instead of a ray. Gets a little trickier graphing it from this into your graph, but same idea. R sine of theta is equal to 2. I'm going to graph this without converting it first. And think about how you would graph this or graph something else when think about how you want to graph it when neither are solved. So right now it's not solved for sine, it's not solved for theta, it's not solved for r. You could go there and solve for these things, but you don't have to. You could do it other ways. I think it's a little bit easier if it's solved. So I'm going to solve for r. The reason I would solve for r is that theta is kind of like the x value. So we normally r depends on theta. R is kind of like the y value. Doesn't mean it has to be, right? We could have it solved differently, but this feels a little bit nicer. I can pick nice values for theta, so that's a good thing as well. Good places for theta. I like pi over 6, so I'm going to say that r is equal to 2 sine pi over 6. And so sine pi over 6 is 1/2. 2 divided by 1/2 is 4. Pi over 6 is also 30 degrees. So 4, we're going to go out. So 1, 2, 3, 4. Okay. Another position that I would go for is 5 pi over 6. That is also at 1/2. So that should also be a 4, or should be 4 for our radius. 5 pi over 6 is 150 degrees. So again, counting out 1, 2, 3, 4. Another one that I would go with is 90 degrees, or pi over 2. So sine of pi over 2 is 1. 2 divided by 1 is 2, which is right there. And maybe you see it from here, but this should just be a straight horizontal line. If you don't see that, that's fine. I probably wouldn't see that if I was starting out with this, but I'm going to now solve for it into rectangular form and show you why this makes sense, and you wouldn't need to go any more coordinates. You can always plug in more coordinates and solve and fine-tune this, but that should be a horizontal line. If we go back to the original equation, r sine of theta, hey, that's exactly y. So y equals 2. Y equals 2 is a horizontal line going this way. This feels weird because it's on circular grids instead of rectangular grids, but again, this is designed more for these types of equations rather than xy coordinates. Again, these mean the same exact thing, just these are drawn a little bit more conveniently for us. Alright, so that one's a cool one. R sine of theta equals 2. That would be one that's simpler to write when it is in rectangular form, but you'll see that we kind of just pick and choose when it's simple and when it's not to use one form or the other. This one isn't as intuitive. If you remember from yesterday's video, we had a similar question and it turned out to be a circle. This is a circle, but you shouldn't know that, or I mean, I would expect you to know that at this point. So I'm just going to solve for it as if we didn't know that, and we're going to make it more recognizable for us. But it's going to be the exact same process as yesterday, so if you want to pause and try it out, feel free. I'm going to give you that opportunity right now. And we're back. So we're going to multiply both sides by r. R squared is 2r sine theta. Remember, that is just a little trick we're going to use because now we have a way to change this into y. We have a way to change this into terms of x and y. Okay. Now here comes the fun part. Get everything to one side. You recognize that you have x squared and y squared, so something's up. You're going to take half of our air quotes b and square it. Add that value to both sides. Half of negative 2 is negative 1. Negative 1 squared is positive 1. So now we have a completed square. We have x squared plus y minus 1 squared. That equals 1. So we have a center at 0, 1, and the radius is 1. That's enough to graph. Center at 0, 1 is right there. I'm going to zoom in on that. 300. Well, why not? So center at 0, 1, radius of 1. It's a little hard to find it over here, so if you want, you can just kind of eyeball it, but it should be that. On this type of graph, you definitely want to have, whenever it's not centered at 0, 0, I prefer the rectangular grid lines, but you should be able to get something close here. If you ever wondered if you could get closer, you can just plug in some angles into the original and solve for r. It's already solved for r, but like if you wanted the degree to be 15 or degree to be 30, I'd probably stick with 30, but sine of 30 is 1/2, so we could go r is equal to 2 sine 30. 150 is another good one. So r should be 1 in this case. So 1, 30. Which looks like my big fat line could count that. Same thing with 150. Should be going through 150. Looks like it's close. So close is good enough for me in this case. All right. Using our calculator. This is the fun part. So we're going to, just like last trimester, we started working with a different mode of the calculator. We're going to work with a different mode here. We're going to work with the polar mode. So we're going to go down to function. I clicked on mode. To go to polar, enter, and if you look at your y equals, it's no longer y equals, it's r equals. R being the radius. So the radius equals stuff. Now with these, you do want to limit, or you have to do more things with your window. if you look at your window, there's thetas involved, and those thetas are basically asking you what numbers should I plug in and when should I stop. The reason you need this is that if I wanted to graph a circle like this, where r equals 3 or something like that, it gets a little difficult for your calculator to figure out where it should start, similar to like your window, but windows are a little bit easier because they're functions. Oftentimes we're not going to be graphing functions with these, except for theta equals blank or r sine theta equals blank, like B and C from number 1. Everything else, for the most part, is not a function. So you don't want to... It needs to know where to start plugging in values and where to stop plugging in values, long story short. So for the most part, so for number 1, and I think for number 2 doesn't matter as much, we're going to go for 0 and 2 pi. So it's going to start by plugging in 0. It's going to plug in angles in between 0 and 2 pi. Our step, we're going to go with pi over 24. That way we get 24 coordinates in there. It should give us enough points. Our x min, let's go with -3. -3 to 3. This, we've already done this problem. We literally just did this problem, so this is where these numbers are coming from. Just thinking of what kind of makes sense. So -3 to 3, and go back to y equals. We're graphing 2 sine theta, so 2, and I don't remember if this matters, but might as well. I want that to be 2 sine. And now if you click this button, it's going to be theta, not x. Graph it. And it shouldn't look very circular because we have our x-axis is stretched out. So if you remember, you can go to zoom and z-square, and it should look like a circle. Centered at 0, 1 with a radius of 1, just like we had it. All right, and then the next one is r sine theta equals 2. Just like you have to have it solved for y, you have to have this solved for r. So r is equal to 2 over sine theta. Go back to this, 2 over sine theta. And it shouldn't really matter what your window is set to. I messed with it because of that z-square thing, but it's still going to be on screen. Hey, it's a flat line, just like we drew in C. So cool, both of those are correct. So this is how you type it in your calculator. Again, the most important part is that you're setting up your theta min, theta max, and your theta step. Most of the time that's not going to change too much. But I think 0 to 2 pi should work for the next stuff. Okay. You ready? 5 new words, at least in math sense. So these are the different forms, or the main forms of polar graphs that we like to talk about in math, just because 1, they have cool shapes, and 2, they come up more frequently. Cardioids look like hearts, and we have some so the cardioids are basically hearts, along with like circles. They kind of look like circles, but with like a little indent. We'll see one in a second. Limesons, I always say these wrong, so if I butcher it and you actually know the way to pronounce it, sorry. But limesons, they're cardioids, but with a loop. So that loop can be either inside or outside of the shape. Or sorry, they either have they kind of look like cardioids, but not exactly. And if you look at their equations, they look very similar. The only difference is that the B value is different than A, where a cardioid, the B value would be exactly the same because it's A in both of those. You can identify if it's going to have an inner loop or not by the order of A and B. If B is bigger, then it has an inner loop. If A is bigger, it doesn't have an inner loop. A rose it's called a rose because it looks like a flower. And you can tell the number of petals, if it's going to be an even number or an odd number, based off of your n value. So if n is even, then there will be 2 times n petals. If it's odd, then it'll have n petals. Just it matches this number, or it's going to be double that number. And this works for cosine or sine. And then lemniscate, again, cool words. These kind of like sometimes look like bow ties or ribbons. I think that word is Latin for ribbon. I don't remember. I might be making stuff up now, but either way, what's new? But again, they kind of look like ribbons or bow ties, I think. But they'll be of the form of that. Nothing crazy about those. Spirals are cool. You should know what those look like. But they have that cool form. E to the power of theta over n. Where n is going to be some positive number. And n is not going to change. You can see in F that it's going to be an even, or it's just going to be a number that's in that fraction. Okay. Let's get into those. So first one is 1 minus sine theta. And graph it. This is a cardioid. Looks like a heart. Pretty cool. Now, the orientation of the heart, whether it's vertical or horizontal, depends on sine or cosine. So you could have one that's kind of on its side, but that is a cardioid. You'll see that a lot of times around Valentine's Day when mathematicians think they're funny. Like always, because they are. Next one, we have 1 plus 2 cosine theta. And this is going to be a lemison. So it kind of looks like a cardioid, except it's one on its side, and it has a little loop in the middle. But another cool graph. So it has that inner loop. We can tell that by looking at the equation, also by looking at the picture. But looking at the equation, the variable or the coefficient of cosine is bigger than the constant. In those cases, you're going to have that. In the next case, 3 minus 2 cosine theta, A is bigger than B, so we're not going to have that inner loop. And again, it kind of looks like a cardioid. It's slightly different, mostly by the steepness of it. It's a little less circular than the others. Okay. And then the next one, we are going to rock 2 cosine 2 theta. 2 cosine 2 theta. Delete that one. Graph it. Here we have a flower, which is, we call those actually roses. And you may have noticed that it kind of doubles over, and it kind of traces over itself. That's, again, why you need to set a theta min, theta max. That way it knows when to stop. Otherwise, it'll just keep graphing this over and over and over and over, and tracing over itself. And so it will just keep doing that, and it gets grumpy with you because it would like to stop working at some point. The next one is a tricky one because it's r squared. So r squared, just like when we have to solve for when you want to graph a circle on your grapher and you don't have a conic, feature on your calculator, maybe you're working with the TI-83, or you don't know about your conic section of your calculator, you have to solve for y in those cases. So in this case, we have to solve for r, taking the square root plus or minus. So we're going to have two equations for this one. It's going to be the square root of 4 sine 2 theta. That's number 1. Number 2 is the same thing, but just negative. Okay, and this is the lemniscate, or our ribbon slash bow tie. And so maybe you saw that little gap that was there. So that gap right there isn't covered by blue, but it is covered by red. Just like this one's not covered by red, but it is covered by blue. That's why you need the plus or minus, just to fill in those gaps. It gets mostly covered by just one of them, but you always want to cover the entire graph. But it looks like a propeller, or a bow tie, or a ribbon. Again, what lemniscate means in Latin, maybe. And last one is my favorite, the spiral. So this one we want to include more spirals, so we're going to change our window, our theta minimum, to negative 2 pi, negative 2 pi, and you'll see that it changes it to a decimal 2. And then we want 12 pi here. And go back. R is already solved for, so we want to hit it with the power of, or e to the power of theta over 8. You can definitely differentiate theta and 8 in there. Again, theta over 8, we're in a graph, and we have a cool spiral going on. Whoa. Yeah, so there it is. But don't worry, I'm not expecting you to be able to graph these by hand. You could, just by plugging in a bunch of different thetas and seeing how long it takes you to start repeating itself. With spirals, they go on forever, or they should, in theory, go on forever. So you're going to be limiting the domain here, but other than that, they should start repeating themselves because of the nature of these problems. Well, that's it for this one. But we are going to start getting into more types of graphing other than polar coordinates. But this is a nice little setup for those things. But I've rambled on enough here. Let me know if you have any questions, but I will see you next time.